will not be taped or anything.
Okay. Looks like I lost some audience, but maybe this may happen. Okay. So I already started to work. Like I summarized now the strategy, right, of this laser method. It's not the full strategy, but it's now the first step. So we should find a tensor T with the decomposition D, right? Think of like a matrix with block decomposition, but everything three-dimensional. And here, so there are all the D components, so all these subtensors that are in the blocks should be matrix tensors. This is property 1, they are matrix tensors. The property 2 is now you just look at the support. So where do you have something non-zero? This is like in this three-dimensional cube, some combinatorial object. And there you want to make sure that you find a large diagonal psi, which is a combinatorial degeneration. You remember, this is this symbol here, and this was achieved by this strange maps ABC, combinatorial degeneration. I will.
And by large, you mean large in Large.
Okay, large means this basically. Okay, so if this cube is ijk, so what is large? Actually, the best thing is this, like if you take the minimum of these 3 dimensions, this is the best. Right. And there's something we see, we try to get close to this, up to a constant factor. This is the meaning of large. And the third thing is we need to know, an upper bound on the T. Best to know it completely. And the experience shows, okay, you hit it when T is a so-called tensor of minimal border rank. So where, like you have like a 5, 5, 5 tensor, and the border rank is 5. Okay, as small as it can get. So if we have this, then, okay, the proposition, I erased it, but it said that the border rank of the tensor that you get by erasing, look here I try to, okay, I have the red and the black things. The red correspond to diagonal, and the black are the one in phi minus psi, and I want to erase all the black ones, okay, by a degeneration. And then this border rank of this guy is at most R. That's the proposition, because it's a combinatorial degeneration. But the point is because it's diagonal, it's a direct sum. And now I can apply the asymptotic sum inequality, or the Schönhage-Tau theorem. Okay, I can apply it. I just use this to get estimate on omega. Okay, so it's this gives some inequality, and then you have a bound. Okay, so.
Can you view it as a device that allows you to bound the rank of other tensors to get a bound on omega? Is that
the bound
high-level point?
Other.
Like this, because the T is not a matrix multiplicity.
No.
That's the whole point.
But no, it's not.
That's not.
We will see this. I will show you the Coppersmith-Winograd examples later on.
I guess what we are struggling with a little bit here is ways of maybe better understanding the motivation behind this degeneration business. If we could get some sort of analogy, maybe not very precise, to help us understand why this becomes a mechanism.
Okay. Do you have, some intuition about restriction? You have one tensor, T, and then you apply alpha tensor, beta tensor, gamma. It's just linear transformation. You get something intuitively. It's smaller or simpler.
In terms of tensors, I
but
kind
okay,
of
but the point is to replace
matrix multiplication. No.
You replace this restriction by degeneration, which is much more flexible for where you say the intuition is. Okay, it's. Okay, if I want to, I want to, yes. So the intuition is this. It's like you have a sequence, okay? Well, actually, a family of tensors T epsilon, They are all. Now this is, maybe I shouldn't put an epsilon. Maybe this is some, what is a good name? M. It's a sequence of tensors. They are all restrictions of T prime, but this is for m in n. But the limit of this thing for m to infinity is the T prime. So this is the topological. This is, you can say it that way, right?
I don't. Wait.
You don't want the prime in the last line.
The last one.
T.
The limit is T.
T. That's a typo. Okay, so but we also have the embarrassing question. So maybe let me go on with my plan, but I understand that I didn't explain this very much detail.
I think there's some idea, which maybe answers the thing, is that first Strassen gave a bound on the rank of the matrix multiplication tensor. And then you saw Schönhage's bound on the order rank of the direct sum of two matrix multiplication tensors. And now you're going to do something even more general. You're going to show how you can use. There will be some tensor which is not even a direct sum of matrix multiplication tensors. You're going to make use of that using this degeneration.
This doesn't explain to me what restriction. Sorry,
Okay,
not restriction. What this degeneration
Okay,
does.
please let me go
We will
on
get
with
to
my
this
talk,
answer.
and we have the embarrassing. Otherwise, I thought, yeah. Otherwise, I will be in trouble with my time. But the point is, there is more to it. I mean,
But we don't know.
for the strategy, we need an asymptotic improvement. So what we are going to do, this strategy is okay, but we will not. If we have this example of T, we will replace T by a high tensor power. So we apply this idea, apply strategy to tensor power. And now there are a couple of things that we should realize. You see, if your tensor has such a decomposition, and you go to a tensor power, it inherits a decomposition, right? I guess you see that. It's like for matrices, you got tensor chronicle products. So apply this to this with induced decomposition. Or maybe I write it d to the n. I don't formally define it, but I hope you see what it will be. For instance, okay? For instance, okay. Let's say, like the simplest block decomposition is just something like that, but it's 3 dimensions, right? I don't draw it. And then you would have, for the combinatorial cube, the side lengths would be this, like bit strings of length n, and things like that, okay? And what you realize, well, how about these components? The components will now be tensor products of such guys here, Tijk, but we know tensor products of matrix multiplication tensors are again matrix multiplication. So this condition will be preserved. We also can handle this because we know the border rank of this, because it's submultiplicative, is at most r to the n. Okay, there's even a potential of saving here something. But so what is the most difficult part here, and this is the most interesting part, is about this 2. So how about getting this diagonal? And we will not find the diagonal here and go to the power. This is not what we do. I mean, the support of the tensor power with respect to dtn combinatorial is just the Cartesian product. Or I mean, again, it will be such a thing. But in such a thing, we have to find a method of producing large diagonals, and this is critical. Okay, now I'm going to write to you how a result, how this is done, and the method goes back to Coppersmith and Winograd. It's really crucial. So I will introduce the notion of a tight set. I think this is 6. Is tight sets. Okay. So the definition. I'm in the combinatorial setting. I have my phi subset of I tensor j. It's general now. Then when I apply it, this will be tensor powers, but now it's fully general. I call this tight if what? Okay, there is some R, natural number, and there are maps, alpha, beta, gamma. This time they are injective, from I to z to the r, beta from j to z to the r, gamma from k to z to the r, and they should all be injective, such that for all I, j, k in phi, now this expression that we had before, alpha I plus beta j plus gamma k, should be 0. That's the definition. Okay, now I know how to, it's a combinatorial definition. I usually imagine it's something like flat in a plane or so, but it's combinatorics. By the way, this is also an exercise if you want to do it. The support of matrix multiplication tensors is tight. It's an exercise. But actually, yeah, right. Okay, I need some parameter. I say this is B tight. B is a natural number if I have some control on the sizes of alpha. So if this alpha I absolute value, beta j absolute value, if they are all bounded by B, okay, then I say B tight. Okay, like. So, and then there's a remark. This notion behaves nicely with respect to product. So if I have phi and phi prime, and they are B tight, and I go to the Cartesian product, you understand what I will do. This will be in I times j times k times I times j times k, but the two i's I put the parentheses. Then this again will be B tight. This is almost obvious. Okay, so then I will replace R by 2R. So that's very easy. So good. So now comes the, maybe I can write it here, the crucial technical lemma. And this is basically Coppersmith and Winograd. But then it was, generalized by Strassen. Coppersmith. So what is it? So it guarantees me, so it says if I have a tight set, then I get large diagonals by combinatorial degenerations. But let me write it formally. I have my phi here, which is B tight. Okay, now there comes a technical condition, which is actually not, I could weaken it, but I write it for simplicity. I assume that the phi is balanced in a way. I mean, it has, I slice it, and in all the slices, in all three coordinate directions, I want to have the same number of points. So if I can write it this way, like P, let's recall this definition, Pi, it goes from phi, it's the projection. It's a projection. So I look what is in the fiber. And this should not depend on I. So this should be cardinality of phi divided by cardinality of I. So it's a balancedness condition, but the same for j. Same thing. So this makes it, this is kind of balanced in this way. And then, if this is the case, then it says there is a psi which is a combinatorial degeneration of phi, and psi is a diagonal. And the size of psi is huge. So it's 1 over b plus 1 times.
Don't write any lower than that.
Sorry?
Don't, on that word.
This is my last line, so. You can read it?
Yeah, but now I'm confused. Doesn't this imply that cardinality of I equals cardinality of J?
Why?
P inverse of J is phi over I, but it's not phi over J, you're saying. So you're,
Yeah.
so I and J.
You're right. You're
play
right.
different
You're right.
roles or
You're right.
something?
You're right. You're right. You're right. This is true. Let's assume that they have same cardinality. I simplify the statement of a more general theorem to make, but in the application it will be the case. I, J, K have same cardinality for sake of simplicity. Okay? You see the point, right? So if I have this crucial lemma, then it gives me a way to deal with this. Okay, so I should talk a little about the proof. I like the proof of this lemma. There are at least two proofs. So one proof is the one with the arithmetic of the sequences free of arithmetic progressions of size 3 with the Salem-Spencer theorem. This is the one thing. But there is another proof. You can read it in the book on algebraic complexity theory, which is actually I like better, which is just with the probabilistic method. So, but I don't have the time to do it, but it's really a beautiful proof. It's a fine example of probabilistic method, but it's not constructive. But it's elegant, right? So, yeah. So I will not prove it. I'll just use it, right?
Neither proof is constructive.
Sorry?
Neither proof.
Well, but this Salem-Spencer theorem is relative. If I remember well, these sets are, it's quite constructive. But this is maybe 30 years ago that I looked at that, so maybe. Anyway, so now after all that, now it's time for the laser method. So the laser method, okay. So,
Just a quick question.
yep,
Don't Coppersmith-Winograd with the Salem-Spencer method show
Sorry?
that we have an honest restriction?
again,
Don't Coppersmith-Winograd with the Salem-Spencer construction, don't we actually get a restriction here and like a just a,
this is true, right? This is true. Very, very good observation. Actually, they did restriction. Okay, so when right, it's restriction. So it's in a way they prove a little bit more. So if you think of practical algorithms, it's much better with restriction. But this is I see this as a conceptual simplification. Okay, if you want to solve the problem and you have more, it's right, correct. It's all true. Okay, so, let me see, we have experts here, the people that know much. I did these things, okay, it's a long time ago. I moved to other topics, and it's quite enjoyable to read your own book. It's quite readable, I remember. I can give this talk, but okay. That's the way, Okay, so good. So laser method, it's the last section. Laser method. Okay. Of course, I cannot explain everything because it's a complicated story. So, but I will put the theorem from which everything, results then. This theorem I need to recall what is the notion of entropy. So P is a probability distribution on my finite set I. It's a probability distribution. So I is a finite set. And then it has the Shannon entropy. I assume most of you know what it is, but let me write the definition. Sum over I, Pi. Log Pi is the entropy. So it's a concave function and it takes its maximum at the uniform distribution. Important in information theory. So, okay, how does it enter? If I have a multinomial coefficient, as I had before. n over mu. So mu is a distribution on S elements, adds up to n. Then the logarithm of them, of this thing, multinomial coefficient, is the asymptotic growth of this is exactly described by the entropy. So it's n times the entropy of, okay, I normalize the distribution plus small o of n. So this is, in coding theory, very, very important. So this is how it enters. Okay, now I state the theorem. This is actually, I think it can fit here. So this kind of summarizes the principle. Maybe this is the science part of the laser method, but there is the more artistic part where it's not so deterministic. But this is the theorem, and this is due to Strassen and Coppersmith-Winograd. Actually, Strassen did something very important. Coppersmith-Winograd improved, and Strassen uniformed. Okay, make it a nice theory and generalized. So, so I have a tensor T with decomposition D, such that, so kind of, these conditions will reappear. First, all the components are matrix tensors. Okay. 2. Now this is now the substitute for 2. Because of that result, crucial lemma, I now require that the D support of my tensor is tight. Okay. And then, okay, that's all. Then I need some space, okay? Okay, now there will be numerical implications, okay? But now it's more complicated for all probability distributions. P on the D support of T, we have the following inequality. Okay, so but here I take the Shannon entropy of the marginal distributions of P. So you see the P is like a three-dimensional object, this support. It's a probability distribution. Then you get three marginal distributions, which I denote P1, P2, P3. And I take the minimum of these. N equals 1, 2, 3. That's a number. Okay. Plus, now, okay, we want to bound to omega. The omega times, this will be, oh, I forgot to introduce some notation. Okay. Hold on. Okay, let me finish writing this, but I forgot to introduce a notation. This is a logarithm of some function zeta, which I will define in a second. So this is this. So there is a strange function log zeta, which I define in a moment, and this is the expectation of this function with respect to the probability distribution P. And this is supposed to be less than the logarithm of the border rank of T. This is the inequality. Now I should write the definition of this function. Okay, I have to erase this, I think. And this is no big deal. I mean, it's just, okay. Yeah. Okay, this I forgot to. So it's just notation. If I have a tensor of format M and P. Actually, Joseph would say I should assume it's concise. Okay, okay. So then these are the dimension parameters, M and P, and I just take what do I take? I would take the geometric mean. So, but if I put here 1/6 instead of 1/3, then it looks a little bit nicer. I call this zeta of T. So the logarithm of this is 1/2 times the arithmetic mean of these dimension parameters. This is this thing. So if okay, let's compute this for a matrix multiplication.
Zeta of ijk in the statement is the product of ijk and k then?
There's a typo. I'm sorry. So this is a component, okay? It's a matrix multiplication tensor. Now there is this quantity which I compute, and if I compute it, it will be this. 1/3. It's basically, think of that. Right? If this is cubic, and then n, then it will be n. So it's like the dimension, or geometric mean of the dimensions. So now you have the expectation of these things with respect to this p. You don't know which p to take the best one, right? Okay, so this thing is, okay, once you are here and you want to derive a consequence, a bound on omega, this is an optimization problem. And the function is good because this is linear in p and this is concave. So it's a convex optimization problem. But for big tensors, it can be very demanding, right? But it's a problem of optimization to exploit it. Okay, so, right, so proof is quite interesting, but okay, I have to think of my time. So I would maybe let me tell you a little bit, like other speakers also do a lot of story and hand waving, a little bit of the spirit behind, and then tell you what are these Coppersmith-Winograd tensors, and probably there's not time for really doing it, even though the proof is not very difficult. The proof is not very difficult. But I think, so there is entropy here. Shannon entropy. Then you think of Shannon. Shannon had his famous theorems in coding theory. And actually, the proof of this theorem is related to proof by Shannon. If you look at it, it's like a Shannon theorem for tensors. So in a way, it's in the quantum worlds. Now I'm talking about things that I don't really understand. Forgive me, okay? But I have been in touch with people doing quantum information theory, and this by assimilation. After some moment you believe you understand things without, and it's a little bit like that. But so this is my view of this. It's like a quantum Shannon theorem, and I just talked to Jeroen in lunch break. It's quite interesting. So Strassen, he did it in the 90s. And at that time, I think quantum information theory was in its infancy. It was before Shor had his famous result. There were some people thinking about that, but kind of, I think it has exactly this spirit. So it's very remarkable. Okay, so maybe no more talk. Let me give these two famous applications. Right, erasing. Where's the thing? Oh, okay, I put it there. Maybe erase this. So there are these two Coppersmith-Winograd tensors that I think I have to write. So there's like the application one. It's, one can say, completely classical. So, okay, people say there is the small Coppersmith-Winograd tensor. Maybe I write T Coppersmith-Wino small. I don't know whether it's standard, but let me write it. It's this tensor. Because, of course, if you want to apply this principle, the question is how to choose this T, and how to choose the decomposition. And this is where, okay, very difficult. So here is the tensor. So I use this notation. I hope you understand. Actually, this is the tensor product of the standard basis vector E0 times EI times EI and so on. It's invariant under cyclic permutations. Maybe it's more symmetric to write it this way. I0, II0. So this tensor, so it has dimension q plus 1, it's cubic. Okay, q plus 1 times q plus 1 times q plus 1. I.
That doesn't pattern match right.
No, what?
The middle one is wrong.
Yeah, that's right. You're okay. Better? Thank you. This is, you know, it's just. It's like for matrices the standard basis is, but in 3 dimension.
But there's a distinguished coordinate.
That's right. So I have I have the basis E0, E1 up to EQ. So I have Q plus. Yeah. And now, you know, I avoid writing 3-dimensional, drawing 3-dimensional pictures because I get it wrong anyway. But you can imagine, hopefully, a little bit how it looks like in 3 dimension. It's like, it's a very flat thing. The support is very smooth. Huh? Yeah, it's like 3 2-dimensional things, unit matrices that you have.
You could use Dirac notation.
Huh?
You could use Dirac notation. That's what
I could.
you use. That's what you
Yeah, I don't
instead
want
of
to. I have jet lag. Okay, I get it wrong. Yeah, you are right. But what is the decomposition? Rather, the decomposition will be like that, fq plus 1. It will be in 2 pieces. It's this. Okay, instead of doing a picture, I do it, just write it this way. Okay, so 2 pieces. So actually, I equals j equals k is just 2 elements. Let's say call them 0 and 1. Okay, so the support, maybe I can, this maybe I can dare to draw. It can be, just 3 points. It will look something like that. This is the support of this thing. Very small object. Very small object. Okay, and this is tight. Very easy to see, this thing. And and this, so this is the support. Maybe I can even write it, okay? I hope this time I get it right. 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, and these components, are very degenerate matrix tangents. So this would be this guy. Okay, I look at my notes, otherwise I get it wrong. But it's something like that, and then I just cyclic permutations. No, they are all the same. No, they are cyclic permutations, and so on. Very flat things, right? These are not true matrix multiplication. It's it's scalar multiplication, another scalar, and inner product. They are kind of trivial atoms. But if you build up the whole thing with the tensor products, you get complicated stuff. Okay, so now I have the tensor, but the border rank of this, I should write, what is the border rank of this? It's not of minimal border rank, but you can prove by writing down a formula that it is the most q plus 2. If it were q plus 1, it would be of minimal border rank. But maybe in the embarrassing questions, if you maybe can try to write down the formula for it. Now, now we have everything to apply this. The question is which probability distribution to take. Now, you see, this support here is symmetric with respect to the symmetric group S3, and then it's a small reasoning to show that if a support is symmetric with respect to this S3, then you can take the a distribution that is invariant under these permutations. So then you take here, everywhere you will take 1/3 because of this additional reason. This will be optimal. And then what will be the marginal distributions? The marginal distributions okay, will be like 1 over 3, 2 over 3. These will the marginals will be. You know, here is 1 over 3 and 2 over 3 in all three directions. Okay, and then if you write this, then you have the entropy of the distribution 1 over 3, 2 over 3, plus omega, and now, okay, I copy it from this logarithm of q should be less than or equal to the logarithm of this border rank estimates q plus 2. Now we have one inequality, and then the question is what q is best, and if you take for q equals a, you do the numerics, then you get the best estimate, and what you get is omega is less than 2.41. This is q. So this tensor is, q is 8. So actually the format of this guy is 9 times 9. Okay. It will be a galactic. Okay. But that's it. You see how it, but this is, I think this is a very clean statement. It's in the book, by the way, on chapter 15. Okay, it's very clean. Now, so this, but now we want to get to the 2.38. No, I will go to the 2.39 because this is humanly doable, right? The 2.39. Okay, I will not have time to. Okay, erase this. So what do you modify a little bit this thing? The small Coppersmith-Winograd tensor. You add one dimension in all three directions. This way you get a tensor of minimal border rank, which is of advantage. Okay, now I see application 2. Okay, now I wrote it yesterday, and then I didn't write many details, so I hope I can do it. I thought I wouldn't have time anyway, but now I skipped many proofs, and I have a lot of time. So it will be here. Now this was q plus 1, now I have q plus 2. I said I add one dimension. Now I have to write it. So what do I have? Before I had the basis vectors E0, E1, up to EQ. Okay, they formed a group. This was a group. Now there's another one. It forms its own group. Okay, and what is it? So I take the small Coppersmith-Winograd tensor, this one, and I add 3 terms. 3 terms. E0, 0, q plus 1. The q plus 1 is the one, the one that I added. But then it should be invariant under cyclic permutations. So that's it. It's like, I don't want to draw it. But, draw it for yourself. You add 3 points. Not somehow skew regard to the others. Okay, so and the decomposition will be now. They are all okay. These are elements. These index sets have now 3 components. Okay, and what else do we need? What is important? What is very important that this border rank of this Coppersmith-Winograd tensor is q plus 2. It's minimal. By the way, it's interesting. I mean, let's assume you could improve this by 1 if it were possible. Okay, then you would get omega equals 2. But it's not true. It is equal. This would make the difference. If it were q plus 1, it would be done. So 1 is missing. Okay. Schade, huh? That's German. Otherwise, we wouldn't be here, maybe. It would be another program. We are fortunate. We still have work to do. Okay, and so, for what else? For q equals 6, I apply the theorem. And for q equals 6, again, now this would be a little bit more complicated because now the support has 6 points, right? But okay, has 6 elements. 6 elements. Okay, and now again, when you want to apply this theorem, you would take a probability distribution. This is invariant under the S3, and then you just need 2 parameters like beta and 1 minus beta, and then you have to do a little optimization in 1 parameter. Let's not do it, but it's just you can do it. I mean, by hand.
In 6.
Huh?
We could do it in all 6.
Yeah.
Yeah, we had to.
Yeah, but you know, I can do it with 1 variable on without computer and anything, and then I get okay.
What probability distribution do you take?
I have to look it up in the book. I don't remember the numbers, as I said.
How do they come up with the probability distribution?
No, it's as I said. You have this. Actually, it's a p is on 6, you know, on 6 points. But because of the symmetry, it's enough to have 1 free parameter, easily figured out. And then it's just this convex optimization. It's just, you know, it's a calculus problem in 1 variable. You can derivative equals 0, you solve it. Actually, maybe you do some Newton iteration. I don't remember. I do not remember. But then you get the 2.39. Now we are in this numerology. You know the Coppersmith-Winograd, they had the 2.38. So what do we do to get to, right? Okay. Coppersmith and Winograd, famous result, unbeaten for, was it 20 years or very long time? I think it's, you know, I think it's 2.37 something, but I really do not care about this so much, honestly. So, what do we do? Is it now something really, you know, what do we do? Or what did they do? Well, they said, how about this one? I think they took this one. But then the analysis is more complicated. But you know, all the assumptions are satisfied. It's just this optimization problem gets more ugly. They stopped. And then maybe 20 years passed and so, I don't know. And then came Virginia Williams and Stotters, improved. Of course, they studied the original papers, and they are kind of, you know, it's a mess. I mean, but basically what they did, now, how about going to higher powers? They realized when we go here, this is Williams, Virginia, and Stotters. I hope I Stotters,
Stotters, but also Legal.
Legal.
Oh, yeah.
The Legal. François. And, okay, as I understand, this problem gets really complicated. You see, what is the size of this tensor is now, we have an 8 times 8 times 8. This is this, okay, this guy. And then the square, 4th power, it's very big. So you get a complicated problem. I don't think you can solve it with off-shelf things. So, but I think this is the main work. And then this was the improvement. There was a small improvement here. But it's this. That's where we are. So, and but there is now, I mean, there has been a lot of progress, but I was not involved in this progress. Joseph knows much more about it than I do. You know, it's kind of magic. Why this tensor? Why? How do you find it? What is special about it? Okay? But there are now structural results saying that why this thing is unique in a certain extent. You can completely characterize, but if you want to know what are these characteristics, you ask Joseph. he knows. Okay? Okay, we try to understand to find other tensors, okay, where these can be applied, but even better it would be have another strategy, but we don't have this. That would be the true breakthrough. But okay, so I think there's no point in giving more technical details when I could, but I would say maybe let's move to the question part now, and then, or if you want to know more details about something I said, I'd be happy to give more details.
Well, thank you very much.
Right, okay.
So now we have questions on his lecture, then we'll have a little break, and then we'll have embarrassing questions on anything.
I'm not easily embarrassed, so I'll ask now.
Okay, good.
I just want to make sure that I sort of understand the context. So a laser method is a method that uses this theorem? Is that
Okay,
right
now this is
definition of laser method?
I think the story is this: you have a really great idea, but you want to sell it. Then you need a good name.
Yeah, sure.
Okay, okay.
Sure,
This is the first
I
thing.
get that.
But
I
I
just wanna know what the
believe,
definition
okay,
is.
I believe my understanding why is laser. But I'm not sure whether my view is this. The crucial thing is, okay, I removed the picture. I see, I had this picture with this thing, how to get the diagonal, partial diagonal, and there is stuff outside that you want to remove somehow, filter out somehow. And I believe, but I'm not a physicist, but this is the idea of the laser, make coherent beam of light, but filtering out other stuff. I believe that's the intuition, but I'm not 100% sure.
Getting rid of all the other frequencies.
So somehow,
Okay.
this is not, that's not a math question, but okay.
Okay, and then part two, and now I'm just trying to remember Jan's talk that I'm not doing very well, which is it known that there is an obstruction to laser methods?
Ooh, yeah, very good,
Know
very
that-
good,
that
very good.
If you have a tensor of
Yeah.
minimal order rank
Nope.
as your starting tensor, and you use this laser method, you cannot prove the exponent.
Okay.
Exponent
Maybe
is 2.
if you can give me 5 more minutes, then
You
I
have
can.
10 more.
Then I can. It's not written, but I thought I will never arrive.
There was another question there first.
Okay, but
Yeah, it's the
then
same
I can.
question.
Yeah.
Also about the obstruction.
Maybe I wanted to say what is. Maybe I can explain it. What is more about this? I mean, what happened to that? I mean, there is this race for the exponent, of course, but maybe there are other things that mathematically are also interesting, and there is this theory by Strassen on his support functionals, and there are the quantum functionals. So, and of course, the question is also what are limitations of these methods? And once you have these quantum functionals, you get obstructions. So Strassen came up with what he called support functionals. Strassen. And then later it was generalized by Cristando, Brana, Zwiedam, who is here in our audience. They call this quantum functionals. And okay, what is it all about? So you want to have, so if T is a tensor, okay, you assign to it a number, f of t, real number. But such that the following holds. You want it to be additive. Okay, you don't have this for the rank. Okay. You want it to be multiplicative. You want it to be monotone. So if T1 is a restriction of T2, or you can also have degeneration, it will be the same. Then you have an inequality here. or maybe you say f of 1 is 1, right? I hope. Where is your room? It's correct?
Yeah.
Okay, good. Okay, so you look at the collection of all these f that have this, and this leads to the notion of the asymptotic
Oh,
spectrum.
you're going too low.
Okay.
Pick another board.
Okay. Yeah. Okay. Such a nice theorem should not be erased.
Well,
Maybe
you guys put it
okay, erase the entropy thing. This way.
Oh, you can slide that one, that's right. Yeah, that's good. Yeah.
Okay.
Oh, is there a board behind that?
No.
No,
No, but you
what
could
did I-
slide that board out to where you
Okay.
can use it.
I want to say.
Oh, good point.
Good.
So Strassen, okay, now, okay, he invented this notion of asymptotic spectrum, which now, people start to get interested after a very long time. It's, in a way, it's the collection of all these nice functionals that have this property. You cannot compute it. I mean, it's, what it exists. It's a topological space, it's a compact space, right? And there is a duality theorem which allows to nicely express what's going on here in all these asymptotic reasonings. Now, I'm not very vague, but, maybe it's later, maybe it's okay. In particular, inside that spectrum, now picture. Now this is, I cannot draw it because I don't know how it looks like, but inside he identified like a triangle, simplex. So there are these 3 points correspond to what? Because, one, an example of f, actually 3 examples. What you can say is, if you have a tensor t, let's say it's here, m1 times m2 times m0 and is concise, then you can say fi of t, defining that mi, the dimension. And when you immediately check this dimension is additive and multiplicative and is monotone. It has all these properties. It's just the 3 side lengths. Okay? And so he managed, I'm improvising, but it was my thesis was about these things. These things that you do in your thesis after 30 years, you still know it. You can kill me, there's just so much suffering, never forget, even if you failed, Okay, so he managed to interpolate between these 3 things, it's very clever. These are the support functionals, but and what I want to say, there is, during these lectures, there was the notion of asymptotic rank. It was defined?
No. I was not going to.
Oh! Okay.
Oh, no.
It was defined.
I did.
Good, it was defined. Okay.
Some of us may not remember what the definition was.
But this, whatever it is, it's 2 to the omega. Like the asymptotic rank of the 2 by 2 matrix multiplication is 2 to the omega. So we don't know the value, right? So what is the rank? You have a tensor, and what is, what was the rank? The minimum R in N, such that tensor is in the sense of restriction less than R. But you may say, instead we can approximate from below. And this leads to the notion of subrank. It's the subrank, Q. Now it's the maximum of the R, such that R is less than or equal to T. So you see, I just reverse. Instead of approximating from above, I approximate with a natural number from below. This is called subrank. And there's a corresponding notion of asymptotic subrank. Okay, it would be that. It's a limit. So you go to the tensor power and take the nth root. If I would have used rank here, I would get the asymptotic rank. But the amazing thing is, while this we cannot compute, this one can. Maybe not for all tensors, but for certain tensors, so that are where the support is tight with respect to some basis, it can be computed by convex optimization. It's very much related to what you see here. It can be computed. So this, we understand, is very exciting. Yes, and due to the work of Jerome, and so we have now a very good understanding, much better understanding what this is than we had maybe 20 years ago. And there are also results on barriers. Maybe there are some, barriers.
Is this the source of some of the lower bounds of the ranks?
Sorry?
Is this the source of some of the lower bounds that you mentioned for the ranks of the matrix multiplication?
This could be used, of course. This can be used for lower bounds, but it's only for the asymptotic. Yeah, it's
These are asymptotic quantities,
it's
not
asymptotic.
for specific.
And we don't know of the only lower bound on a tensor we know in the asymptotic regime is the dimension. It could be that for every, let's say, a cubic tensor of format n and n, could be that any tensor has asymptotic rank, and we don't know. There's even a conjecture by Strassen for tensors with tight support that it should be n. So the theory, so it's kind of, is it good or bad? It would be disappointing, maybe.
Yes.
But I wanted to say, maybe I should really finish. I mean, if you want to explore the limits of that, I mean, is it possible to hit omega equals 2 with this method? There are some abstractions, and this is work where also Jerome is an author, where you use this functionals to understand this, and I think it becomes very clear. Yes?
So just to understand why we can't hit omega equals 2 with this, there must be some like epsilon that we can't hit omega plus epsilon, right?
I thought he was going to write is if you take the ratio of r tilde over q tilde, a necessary condition to be able to use this theorem to prove omega equals 2 is that ratio is 1.
That's right. So this ratio is a logarithm
if
of...
the ratio is greater than 1, so in particular, r tilde has to be minimal and q tilde has to be maximal. And since, like Peter said, in some case, we don't know how to compute r tilde for any non-trivial example, but we do know how to compute q tilde for tight, in principle, at least for tight tensors, and that's how you prove that no minimal border rank has maximal q tilde. There's a bunch of work on that.
There have been many papers by many,
Yeah.
But basically, it's the way I didn't read all these papers. Okay, disclaimer. But I believe this what's actually going on is captured by this. So this is called irreversibility, and Jerome knows more about it, right? Is it? I think so. So I want to say everything becomes very clear. We don't know what is omega, but if you have this framework by Strassen, it's just very clear mathematics. Okay, all of the engineering parts kind of, have been removed in a way. Okay, question, yes.
Not regarding that part, but maybe one step before. So you said heuristics show that we want tensors of minimal border range.
Yes.
Is that just heuristics or is there a theorem?
I'm not aware of a theorem.
Because like the obstruction, to my understanding, applies to minimal border range, right? But we don't actually know if we need one.
I don't think there is a theorem. I'm not aware. Maybe you know?
I didn't understand.
My question was whether there's a theorem that we actually want to use at tensor of minimum border
Well,
rank.
if you look at this theorem here, you want that right-hand side to be as small as possible. So if RT is minimal, then you,
Yeah, that's heuristics, right?
that is heuristics.
But yeah, I mean, maybe we need one, but maybe there's some contrived example where it's not minimal border rank.
Well, yeah, but then you're going to have to probably prove some better estimate than its actual border rank.
Okay, but yeah.
Okay. Other questions? Oh,
Very simple. So over there on that board next to quantum functionals,
Yes, here.
some names.
Christandel, Vrana, Zwiedam.
Okay.
So this is
What about this?
Jeroen Zwiedam is here. Yeah, it's here.
but that's not the
will that
correct
help-
pronunciation of his name.
Zwiedam?
That's okay. That's
What is the correct?
well, it's Zuidam, but that's fine.
Okay, and so nobody ever told me. I
I
said,
just want to be able to spell
even
that.
his first name is difficult. Jeroen. I learned it after 3 years. Then I realized people, you know. By the way, you also misspelled my family name.
Now it's the
human.
time for payback.
Okay, so maybe since we are here the whole semester and we will run seminars, so I think it will be really great to in one of these, a couple of seminars, to, you know, revisit this Strassen here of this asymptotic spectra, of the support vector, of the quantum functional, because I think it's great and there are interesting open questions and maybe there can be some progress on that. Because I had the impression that this was laying dormant for decades, but probably there are many treasures to be discovered, I believe. Okay.
But we should probably take a little break before the embarrassing question, so let's thank her again. In 10 minutes.